So we're going to go ahead and get started here. And just as we get rolling, we do have a couple schedule changes that were unintended. So evidently, one of our speakers, Suresh Jagannathan, came down with laryngitis. That evidently makes it difficult to speak, is what I have been told. At least that's what I was trying to talk to him on the phone. That did not work out very well. So he's been dropped from the schedule, and then also the AFRL speaker will be Dr. Derek Kingston, and he'll be talking about some of the results for Summer of Innovation. But to kickstart this, we have Jim Paduano from Aurora Flight Sciences, and he'll be giving a talk here on trusted autonomy in the cockpit. We are live streaming this today on YouTube Live. And so there are, I know folks in Portland and Mississippi State and Arlington and other places are watching this online. So, Jim?
So can you hear me okay? No. Okay. Like this? Better? Okay. I'm Jim Paduano. I work at Aurora Flight Sciences. And when I was asked to speak today by Galois, who are experts in cyber, I said, do I have to talk about cyber? Because I know nothing about that. And they said that was fine. I'll talk about how trust is related to cyber, but I'm mainly going to talk about things that Aurora knows about, which are unmanned vehicles. I'll talk about Aurora's business areas, then I'll define trust for the purposes of this talk. I'm not trying to say the last word on trust. And then I'll give some examples of that and try to be a little bit prescriptive about things one can do to get trust going in the UAV examples that we deal with. So Aurora designs, builds, and operates advanced autonomous aircraft. UAVs of all kinds, and we've crossed the whole spectrum. Okay. Right there. Okay, here we go. Not used to using microphones, obviously. Where was I? We go across the whole spectrum of R&D, manufacturing, and operations. So I'm not going to spend a lot of time on this. I just want to say that I'm from the R&D side of things, and the R&D sector is based mainly out of Cambridge, Massachusetts, and these are the 5 core technology areas we work on, autonomy being one of the main focuses. So what does trust mean to Aurora? For us, we basically want to be a trusted UAV provider. So we deliver high confidence that our systems will operate as designed. Obviously, that's a mantra in the aerospace community. Everybody wants their systems to be safe, reliable, and robust to disturbances. In the context of autonomy, disturbances can take many forms. So normally we think of flight control systems and disturbances like wind gusts and so forth. What I'm really talking about is things that can make software go bad, such as bad actors, error-prone coders, and real-world non-idealities, which is where I'm going to spend most of my time because that's where most of my background is. So, trying to build up a little bit of a hierarchy of trust. Start sort of at the base layer, trusting that the underlying system has not been tampered with. So this is not something that people used to worry about at all, but now it's a big deal, cyber secure. Once you've laid that framework or that groundwork, you want to trust that the software itself operates as designed and that this design meets the customer's expectations. So trust is really translates into verification and validation. So many of you are familiar with that, and this is where most of the work has gone on in the dim, distant past. What's at the top level of trying to understand trust and autonomy is the operators, the people that use autonomy, the people that watch autonomy do its thing, and there are always humans involved, and you really don't want the human to ever ask, what is it doing now? So you'd like the users of the autonomy to have enough trust in that autonomy that they will delegate authority to that autonomy. And the Defense Science Board basically defined autonomy as the ability to take that authority and act on on it independently. So I want to focus on this because this is something that's a very sort of established science. This is something I know very little about, and this is more having to do with autonomy itself. So I want to talk about this in the context of two examples that Aurora has worked on. The first is the Alias Problem. Now this is a DARPA-funded effort to create a robotic co-pilot. And I won't go into the details of the reasons why you might want to have a robotic co-pilot, but the idea is that this is second person in the cockpit that's communicating with the main pilot and helping execute all the functions that make a aircraft into an autonomous vehicle. Just happens to have people in it performing those functions and creating that autonomous capability. So what does a co-pilot have to do? They have to use mostly vision to understand the state of the vehicle, the configuration of the vehicle, its location in space, its orientation, and its situation in the airspace. So all of that is information that can be gathered mainly by looking at instruments and looking out the window. All of this translates into some decision about how to point the vehicle in the right direction, right the vehicle from the attitude that it's in, and go where you want to go. Then you need to actuate. Mainly, people think about the stick and rudder, flying the aircraft, but what happens now in aircraft is more often switching switches, configuring the aircraft, doing dialing in the radios and so forth. So there's a lot of manipulation to be done in a typical cockpit, and DARPA asked us to do those things. Finally, and perhaps most importantly, the co-pilot has to work with the pilot to create a team that effectively carries out all the functions required to fly the aircraft. And coordinating all of that, applying judgment, training, and knowledge is the focus of the brain. All of this can only really happen if you have knowledge, if you have some understanding of the airspace and how an aircraft flies and how to configure it to get to the next phase of its flight. So we do that by something we call digital type rating files. A type rating is what a pilot will get when he learns to fly. He or she learns how to fly a new aircraft. So you're rated to fly a certain type of aircraft. If we have our Alias system gets rated by reading the appropriate files. So those files include the flight dynamics, the pilot digitization of the pilot operating handbook, which includes emergency procedures, all the positions of everything in the cockpit, so you know where to look to learn about the vehicle configuration, operational knowledge, and how to look at the gauges and interpret them over time, how to determine how the engine is performing, what's happening with the communication systems, and how to approach a landing site. All the details of what a pilot has to know, and it's a vast array of things, and capturing all that knowledge is a very big job. So to do that, we basically created a system that has cameras for perception, robotic arms and legs, a universal robot to switch all the switches and handle the throttle, an actuator for the yoke, rudder pedals, so forth. The Autonomy core, which is how to fly knowledge and interconnection of all the system, and finally a human interface, which is essentially the face of the pilot, and the method by which Alias gains trust of the pilot and becomes a team member with the pilot. So that's the example. There we go. This is one instantiation of the Alias pilot flying a 737 through an emergency procedure where the assumption is that the pilot is hypoxic. There's been loss of cabin pressure, he doesn't have enough oxygen, he's no longer able to fly the aircraft. And so the system is dialing the FMS, changing the airspeed, the altitude setting, moving the throttles when you get to the landing stage of the process, and basically doing all the functionalities required by required of a pilot in an aircraft that's highly automated already. So all of this was All of these functionalities that you see were integrated into the aircraft through the knowledge acquisition system. And so this is just an example of how these robots fly aircraft. So how do you get a pilot to want to have this robot next to them? The answer is you might not. You might not ever get a pilot to actually choose a robot over a human who they've worked with and gained a rapport with and trust very implicitly with their lives with this robot that barely knows how to do what pilots know inherently. But there are some things that you can do to try to overcome the barriers to trust. One is to operate in a logical and predictable manner. So obviously you need to be secure, you need to have verification and validation, but more importantly, you need to be the pilot needs to have an internal model of what his co-pilot is doing at all times. Things behave the way he expects, there's no strange behavior. This usually means the system is too simple and can't do anything very interesting. And so there's a dichotomy there, simplicity versus utility. Another way you can try to develop a rapport with the pilot is to give them ownership. Just like you own your cell phone, you configure your cell phone yourself, you decide what function it's going to do for you, you turn things off if they're annoying. So, and this is one of the ways we've set up our application. There's a roles page. You'll take this role, I'll take that role. Certain roles Alias can't do. It's not capable to do those functions. So there's kind of a electronic flight bag feel to it if you're familiar with those. Pilots really love their electronic flight bags. They contain a lot of information that they need, and then they can pull it up when they need it, and it gets populated automatically. And so in that context, the ownership of that tablet, which is the interface to the robot, is important. The dichotomy there is that if your main purpose, one of the main purposes of a co-pilot is to cross-check what the pilot is doing. And it's pretty hard to get value out of a computer or a robot over a human if you don't take advantage of its ability to very diligently stare at the instruments and look to make sure things are in the right configuration. But doing that in a way that's not annoying is very difficult. So there's the likelihood that the pilot will just turn off those functions. So checking and reminding versus being annoying and being turned off is definitely an issue. Finally, well, I have two more. The next is user testing. Can't stress enough the importance of this, and any company that works on user interfaces or apps knows that you can't get away without doing a lot of this, and getting the roles right. In the case of a pilot versus co-pilot, if we try to replicate the way a pilot interacts with a co-pilot, we're almost completely doomed to failure. The pilot is going to interact with the robot in a different way than they interact with a co-pilot. It's just the nature of relationships between people. You don't try to replicate those one for one. Problem with testing is it can be very costly. I'll talk a little bit about how we try to reduce the cost of testing of autonomy. If you don't test enough, the result may be subjective. And finally, some people think we just need to wait for the next generation of pilots, because younger generation of people are not that averse to having robots in their lives, whereas people like me don't even like Google telling me which way to go. So here's an example, and I'm going to go through this very quickly, of how we do the knowledge acquisition, because it's kind of a lesson learned about pilots working with robots. The pilot has to do something called a checklist to start the engine. This is in the pilot operating handbook. We applied happens to be the checklist for this DHC-2 Beaver at the U.S. Navy Test Pilot School, which is one of the aircraft on which we installed the Alias system. So if you try to run through this, if you try to watch the pilot run through this checklist and make sure they did it properly, they will hate you. You're not doing it they do things in an order that meets the intent of this list, but does not follow this list prescriptively. So you actually have to look at how a pilot does it. You have to learn from a pilot what can be done and what can't be done in different orders. You have to be trained, just like a pilot has to be trained to start that engine. This list by itself is not enough. So this actually turns out to be the flow diagram of the decisions the decision points that need to be made gone through to carry out this checklist. So we encoded this and we've got this set up. The problem is that getting this to run as smoothly and as seamlessly as a pilot and co-pilot cross-checking each other is almost impossible. So the lesson learned, we do have a procedure editor for doing this. This procedure editor allows us to do interesting things, but this might not be the best application because pilots just don't want to be bothered with something they do very mechanically or very intuitively and very quickly, and having a robot that doesn't quite get it involved is just an annoyance. So those are some of the lessons we learned about trust and autonomy on the Alias program. I want to talk about another program which has an interesting historical connection. Elevators. I shouldn't have done that. So elevators used to be devices that needed an operator. Nobody got in an elevator without having a guy standing there to run the elevator for them. Now, nobody even thinks about that being a thing. You push the buttons, it takes you there. And Uber very cleverly used the same idea for the Uber Elevate concept. They didn't want to use the word taxi, so they decided that they would use the word elevate, where you're trying to get from point A to B, which is what an elevator does. You want to climb into a device, push some buttons, or have already told the device where you want to go on your app, and just sit in and have it go there. So this is Aurora's concept for the Uber Elevate vehicle. It's fully automated, and it takes you from point A to point B. The thing that's not shown in this video is that in order for the Uber Elevate concept to be economically viable, you have to have thousands of these things flying at the same time. So here's a nice pristine environment, one vehicle taking on its mission, no contingencies happening, nothing going astray, blue skies, and it's a relatively straightforward autonomy problem. But in reality, there's a lot to think about here, and not the least of which is getting people to trust that this system is going to work the way it's supposed to work. So that's what I want to talk about today. Let's see if I want to play the rest. Yeah, so here it is coming in for a landing. So I can talk a lot about why this is the best Uber Elevate vehicle you can possibly imagine, but I'm going to just talk about some of the unique issues that involve trust in the Uber Elevate mission. The first is that the airspace itself needs to be redefined. There's no equivalent for the way these things are going to operate in the current airspace model. And people take the airspace for granted. They trust that the airspace is safe. There's people managing and monitoring the airspace all the time so that it's safe. But we don't know exactly how that's going to work in a rooftop-to-rooftop type model. And the number of people involved on the ground watching the airspace has to be sufficiently low to make it an economically viable model. And so that's gonna also be a big trust factor, essentially saying I'm gonna have one guy on the ground responsible for 10 or 20 or so vehicles that are flying through the air. The first adopters are going to be very different than the ultimate users. The first adopters will probably be paying enough that a pilot can be in the cockpit, and you can turn to the pilot if you want to go to a different location, or if you get sick, or if there's some decision that you would like to interject into the process. But once these things need to be scaled, you still want to have someone that you can turn to, just like the elevator call button. You know there's an elevator call button there in case the elevator has problems, and you'd like to have a similarly safe feeling about these devices. Finally, the humans on the loop, the people watching as they sit there, this autonomy taking them from point A to B, they do have responsibilities. Even in current air travel, you have certain responsibilities. There are certain expectations. You're gonna buckle your seatbelt. You're willing to carry out certain emergency functions if necessary, and you're in some sense responsible for your own safety in the vehicle. What is the role of a human in an Uber-like context, and how do they gain trust that they have sufficient safety and can carry out those roles? And similarly, what are their options? If they at some point want to change what's happening, could be for a personal reason, could be for an emergency reason, what are the options that they have? So these are some things that we're tackling right now in our model of how autonomy works in the Uber Elevate class vehicle. How am I doing on time? All right, that's where I kind of want to wrap up. So in order to tackle that, we're making autonomy a context-aware team player. Basically, context is understanding what the situation is, what things could be driving the system away from nominal operation, and what ought to happen next. Communication of the subsequent autonomous attempt is key when there is no experienced co-pilot in the cabin. So you're going to have a large range of people, starting from early days pilots that operated the vehicle all the time, all the way up to people that have never even climbed in these things before. And finally, input from the user intent must also be seamless. So you have to have a naturalistic way to interact with the system. To test these kind of things, we have a platform that's specifically oriented toward behaving like an unmanned vehicle, but having people on board to monitor the system. So this is our optionally piloted Centaur. It's a civil aircraft with a robot in the right-hand side, with a pilot sitting next to them, making sure that the thing is flying properly in the hybrid mode. So it allows us to test in various scenarios with various different ways of interacting with the autonomy, and it's very low cost compared to other approaches. And we have an autonomous system that sits in the middle of that drives other systems at Aurora, and built on verifiable software base. So that's where I'll stop. Would like just to close by saying that trustworthy can mean correct, resilient, and safe, but it also means exhibiting behavior that inspires confidence, which seems kind of wishy-washy, but it's very real, it's very important. Users are in charge, and they want both of those things. One without the other, in the first case, leads to accidents. In the second case, basically nobody's going to use it, nobody's going to want it, and you've just wasted all your time. So thank you very much.
Thanks. So next up will be Derek Kingston with the Air Force Research Labs, and I'll get his slides pulled up here, and this is the clicker.
So maybe a bridge between my talk and Jim's. Jim talked a little bit about what trust meant in his context, and the context that I'll be talking about is essentially in terms of how do we as institutions, at least from my perspective as AFRL, how do we as the Air Force trust that the software that we've built, the aircraft we built, are safe? So it's in some sense, how do we get through that verification and validation process in a way that allows us institutionally to trust these vehicles, and of course then there's the psychology of humans in the cockpits, et cetera, et cetera. But just to, I guess, set the same context, that's what I'll be talking about primarily. So here we go. Awesome. So Jim, you mentioned that, hey, this is well-established science, we know how to do it. Which, definitely there's a lot of history here. So I'll talk a bit about what are the new frontiers for us and what we're researching in particular on pushing the boundaries on verification and validation. So the first thing I'd like to do, though, is just point out that this is in the context of autonomy, right? We want to trust it in some sense, and like I mentioned, institutionally trust that the software we've written is going to be safe, reliable, performant in some sense. And this is the autonomy strategy for AFRL. And the couple of things I want to point out, so the first one is sort of this flexible autonomy. You want to be able to do lots of interesting things and do it rapidly, replace things as you upgrade in some sense. But you want to do that with goal number 4 in a safe way. So there's a little bit of competition here in the sense that, hey, we want to run fast and do lots of interesting new things, but at the same time we want to remain safe and make sure that we're handling the situations appropriately. So this is my one chart to kind of motivate why you might not want to do things if you've always done them in this space. And let me just, I guess, point out a couple of different things. The first, here on the right, is a picture of the Mars Science Laboratory, Curiosity. And if any of you have seen their landing sequence, if you haven't seen it, you should go look it up on YouTube. It's really cool. It's like this 4-stage landing that has like a booster thing and a parachute and an inflatable ball. It's really cool how it lands. But the point is that the software to automate that sort of thing, just the landing alone, the software on that vehicle is more than all the other software they've ever written to get to Mars. So the size of the software base is growing extremely fast. In fact, we see the same thing in commercial aircraft. This graph down here, this is actually a log-log plot, so it's growing exponentially. The number of lines of code on commercial aircraft. The end of the story for this paper in particular, that this graph is pulled from, is that we're pretty much at the limits to where we can do our traditional verification and validation of this kind of software for the size of code bases that are running on modern aircraft. And if we don't do something differently, we will simply run out of time and money to do it the standard way. All right? And another interesting way to put this is a study that was done by RAND in 2016. This study actually just mirrors a study that NASA did in 1992. And the study really says, hey, if we want to replace a human system with an automated system, and we just want to show statistically that our performance is as safe, then what will it take? So this study looked at how often are there fatal car accidents across the entire United States, and basically per mile, what's the chances that you die and that somebody's killed in a car accident? And then if we want to be able to show statistically that our autonomous system is as safe as a human, how many miles would we have to drive? And so they just ran the numbers, and it turns out you have to drive 11 billion miles to do that. Right? That's an enormous amount of testing. If you had a fleet of 100 cars, it would take you 500 years to drive 11 billion miles. Right? So testing alone is not going to save you. Right? Certainly we want testing, but if you rely solely on it, you won't be able to, I think, answer the mail in a lot of these ways. So, what's to be done, right? So we have, I guess, a couple different solutions that we're trying to push. The first is move a lot of this verification and validation into the design phase. So this is your traditional sort of systems acquisition chart, going from like requirements all the way to transition, and in somewhere in there you need to show that what you built actually met the requirements that you specified, and that's where you're doing your testing, verification, validation. It's all the way over here, right? And I guess what we're suggesting is that you need to move a lot of the thinking about this to the left. You need to be thinking about how you're going to test it and verify it as you design it. Otherwise, it will be very expensive to solve it at the end. So this is just some numbers from what it takes to do software fixes. Essentially, if you're fixing things, you're finding failures at the end of your process, they're 1,000 times more expensive to fix than if you had found them up front. So moving whatever formal techniques or good techniques about this over to the left is going to save you a lot. So that's one approach, right? And the next I'll talk about it in a couple charts. So this is our process, or our proposed process for how you might go about, instead of doing just a linear design where you identify requirements, build the system, and then test it. You have more of an iterative design in the requirements formalization, and you actually apply some interesting tools at this level right now, at the requirements level, at the architecture level, to say, yes, we've got things correct. We're not missing important pieces that we know we're going to have to test later. And there are lots of interesting techniques and tools to do this, to describe software architectures and the interactions of software in such a way that you can say properties hold about that software. And once you've done sort of this iterative design and requirements phase and architecture phase, we're suggesting that you have multiple verification validation paths. One is your traditional, simulate it, test it, evaluate it as normal. But then there are other ways, right? You might have mathematical proofs about correctness of your software. Or you might have other techniques for bounding the behavior of that software, and then you can argue about the behavior bounds rather than the behavior itself. In other words, I might not know exactly how my software works, but I know if it ever tries to get outside of some fence that I've established, I can cut it off and I can prove, or at least show with lots of testing, that my fence is solid and secure. And then our idea is that hopefully that can all be argued to some degree in a certification case, which can be reused the next time you build a system. So that's sort of our overall vision for how you might get this flexible autonomous system, but at the same time have safety as you design. And we work collaboratively with NASA to define some of these processes. Okay, so if you look in the back, there's a big poster for Summer of Innovation. This is a project that we ran this summer. My team at AFRL, we basically hosted 50 participants across 16 different organizations. The idea was to take some of these ideas, this strategy for verification and validation of autonomous software, and actually apply it to software that AFRL had written for multi-vehicle control. So we started with an established software base that does searches, basically surveillance tasks for multiple aircraft. And then we wanted to apply these cutting-edge tools for verification and validation to that software to see what we could learn about the applicability of these tools. This all concluded with a special session at S5. This is a conference that my group runs here in Dayton that happened in August. So from May until August, 12 weeks or so, there was this sort of intensive push from 50 people to try and apply this. Again, kind of with the answer, we wanted to answer, how applicable are these tools to, in particular, the multi-UAV autonomy domain. All right, so what did we do? So over the summer, we did exactly what I said at the beginning of that iterative loop. We formalized requirements, so we wrote them down precisely, unambiguously. We tried to write them down mathematically in some ways that we could show properties about those requirements. We built a formal architecture in a language called ADL, Architecture Description Language. We applied some methods for proving safe and correct behavior through techniques for mathematically showing that the algorithms you're using are actually correct. We did some cybersecurity improvements to the software. In particular, we're trying to guarantee some memory safety properties and some timing properties. In other words, that things that should run on time. There was a large team that was focused on testing. How do we use testing smartly so that we don't just test everywhere, we test in the places that we know we might have trouble. So you want to sort of be smart about automated testing. And then we're arguing about all these things. How are we going to actually convince someone that we've done this correctly? We have a runtime assurance paradigm in there. The idea here is what I was describing is sort of that fence that you can't cross. So we added that to the software. So if it tries to break out, we can contain it. We did a lot of work on hybrid systems analysis. That's sort of where the software meets the actual physics involved. There's a very interesting interplay there and some interesting research to be done. And finally, we actually improved some of the automated techniques for planning. So I wanted to just pull out one of the highlights from the summer. This is sort of that memory safety property. How do you get memory safety for your software? The answer is it's really hard. DARPA recently concluded a program doing this for basically from scratch. It's the DARPA Hackams program, and we leveraged that technique for our software. The idea is you've got UXS, this is our software running. It's unproven, unknown, but you put it on top of a safety critical operating system. So this operating system has been formally proven to be memory safe, and then we're running UXS in a virtual machine, so it's not safe. But we're going to extract a part of it, a critical piece of it, and then move it into the memory safe area. So the idea would be that if a vulnerability happened here for whatever reason, because the operating system is not secure, because our connection to the external world is not secure, or I've written bad code. For whatever reason, this part crashes. Because of the guarantees that I have running on this secure operating system, I know that the rest of it might be compromised, but my critical system will still run. So we sort of extracted a key piece of the software, placed it in the secure environment, then proved its behavior to say that, okay, we can mathematically say that its behavior is correct, and then we can leverage the guarantees that says no matter what compromises the Wild West part of this architecture, the safety critical stuff remains. And then we demonstrated this by actually cyber attacking the VM here, crashing it and showing that we could still operate. So where are we going next? We're trying to take a lot of the lessons that we've learned from this summer and continue to apply them to our software. Basically, we took some incremental steps. We learned a lot about what the right directions might be, and we're going to continue pushing on this. I don't know if I'll cover all of these, but maybe one thing I want to point out is we're involved in a working group with the airworthiness experts at AFRL and the Air Force level to try and mold the system in such a way that these kinds of techniques can be adopted. Otherwise, you'll have to do traditional test, verification, validation, which might, as I mentioned earlier, take a lot of money and time. So with that, I think I will take questions, if there are any. Thanks.
Cool. Thanks, and for those that are online, we realize the slides are a little askew, but and we'll get that fixed for the next set of talks. But if there's any questions for Jim, if Jim, anybody have anything for Jim that they want to ask him, feel free to grab him afterwards. Derek will be around here, and otherwise just hang out and have some additional conversations. Thanks.